Hello. In this online lecture, we're going to talk about OS operations. Now that we know theoretically what an operating system does, let's talk about the nuts and bolts of how it does it. And when I say nuts and bolts, I actually mean nuts and bolts. We're going to talk about the bits and bytes of the operating system, the actual core operations. So let's get started. There are, so right off the bat, we're going to start with a joke. There are 1-0 type of people in the world, those who know binary and those who do not. That's because in the world of binary, 1-0 equals 2. So we'll talk about that in a little bit. We're going to talk about, these are the subjects we're going to talk about in the next couple slides. We're going to talk about decimal versus binary versus hexadecimal. Hopefully getting you a little bit more comfortable with those concepts of having different number systems. They're not as complex as one might want them to seem. We're going to talk about bits and bytes, which is kind of how we store the binary number system, which is what computers understand. And then we're going to talk about units of storage of the various units that we store our bits, and bytes are kind of a unit of storage themselves. And nibbles. So we'll talk about those subjects right now in the next couple slides. Let me get back to my slides. There we go. So we're going to do some the decimal versus binary versus hexadecimal. So in the world of decimal, which we grew up with, and by the way, most of us have 10 fingers and 10 toes, and we're taught to count by tens, and that's normal to us. And the only reason why it is normal is because that's what's been from day one. But we got our 1, 2, 3, 4, 5, 6, 7, 8, 9. Those and 0, right? So those are the 10 digits that we are told about, right? And then, of course, when we hit 10, we just simply say, well, we're out of digits, right? And we'll just take the 1 and the 0, and we'll start the process over, right? And then when we get to the next one, we'll go to 2 and 0 and start the process over infinity, right? And it'll just keep going from there. And of course, for us, that's completely normal. If you hit someone the number 1, 9, my 9 got a little messed up there, 2, 3, our brain automatically translates that to 1,923. No big deal. Well, computers are kind of very similar, except for they have the 0 and they have the 1 off and on, right? They either have the electronic signal or they don't have the electronic signal. That's essentially the basics of it. And by the way, this is a bit. We're going to talk about that a little bit, but the simple storage of data, 1 or 0, is a bit. Right, but so the question happens: 0, right? Let me do this a different way, right? 0 equals 0. So far, so simple. And I'm going to translate it over to decimal, right? So, and 1 equals 1. If you see 1, it's going to be a 1, right? But then binary, so here's our binary world. Here's our decimal world. What happens is binary runs out of numbers. And just like when we run out of numbers, we just simply move 1 over and we use it. So that's going to equal 2. There you go. And then, next one would be 3. And then what happens is we've run out of digits again, so we need to move over another space. And we're going to go 100 or 100, and that equals 4. There you go. Infinity. It goes from there. One easy way to remember the binary translation, moving over translation, is, as you can see, every time you jump over a position, there's going to be a pattern to it. It's going to be powers of 2, which makes sense because there's only 2 digits. So math is predictable like that. These powers of 2. So if I again went over here and did 101. That equals 5, right? If I go 1, 1, 1, 0, right? That's going to be 6. 1, 1, 1 would be 7. And then the next 1,000, or 1000, would equal 8. Okay, so what ends up happening is, again, we're using the power as a 2. The positions are going to be dictate what that number is. So what we often do to translate that is what I like to call the Rosetta Stone of decimal or binary. So what we're going to do is 1. The first position's 1. The second position's 2, and I'm just going to do power as a 2. And we'll go up to 8 bits. We're going to go up to 8 decimal or binary positions. Okay. 1, 2, 4, 8, 16, 32. I'm running out of room here. 64, and then we'll just be able to squeak in 128. All right. So using this binary transition, right? I can put any number in here. So let's just come up with a number. I'll make it 1, 1, 0, 1, 0, 1, 1. First of all, I know it's an odd number. The only way to make an odd number is to activate that last 1. And I can just add all these up. So 1 plus 2 is 3, plus 8 is 11, plus 32 is, I said 11, so 43, plus 67 is, 60, I'm sorry, I was already doing the math in my head, plus 64 is going to be 7, it was 47, so 107. I should double check that because I got a little distracted as I was doing it. 1 plus 2 is 3, plus 8 is 11. Helps to make little cheat codes appear. This is, of course, is 96. And there you go, 107. So there you go. And you can just, that works for any number. You just plop it in here. Again, the zeros, just like the decimal world, you can put as many zeros as you want in front of something, right? So there you go. If I do 1, 1, again, back to what we were talking about, equals 3, right? If I want to do something more difficult, remember, if I want to turn all these on, by the way, and you're going to see this a lot in networking, that would actually equal 255. Okay, I have that memorized, believe me. Subnet mask. Anyway, long story short, that is how binary works as a number. So if you just give me any random number, I can plop it in here. Now this is for 8 bits. Again, this would go into infinity, and I would just simply keep doubling it, be powers of 2. So this is, 2 to the first power, 2 to the second power, third power, well, 2 to the first power. 2 to the second power, 2 to the third power, 4th, 5th, 6th, 7th, so on, right? So the next number would be 256, number after that would be 512, 1024. It would just keep going on, all right? And you can make any number you want with 1s and 0s. And by the way, that's your cat video, right? The cat video is all 1s and 0s. This is the only thing a computer understands. Now, because the world of computers, we're going to talk about bits and bytes in a second and nibbles. But know this too, there's another system called hexadecimal. All right, hexadecimal, what it's going to do is it's going to have, well, 0 is going to equal 0. All right, that's good. It's going to have 1 is going to equal 1. 2 is going to equal 2. All right, it's going to keep going on, dot, 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 all the way till we get to 10. But in order to save space, let's just say, and we want to write out very complex numbers, what we're going to do is we're going to utilize letters. Okay, so when I do A, all right, let's do, just for simplicity, I'm going to make a 9. 9 equals 9. Okay, and then 10, so over here, this in the decimal world is going to be 10, but in hexadecimal it's going to be A. All right, and then B is going to be 11. That should be a 2. Sorry, I think RAM is starting to give out on me here. It's starting to slow down. C is going to equal 13. A, B, C, D is going to be 14. And finally, F is going to equal 15. All right. So hexadecimal is going to go from 0 to 15. Oh, not equal. That should be a line. All the way to 15. All right. So 0 to 15 is hexadecimal. without explaining how nibbles and bytes work, I can't really give you the translation of how to move it around, and it's not really important in an operating systems class like this. So just be advised that hexadecimal has characters that are going to be 0 through 15. I'm sorry, well, it can have up to 15. It's going to be 0 through F. So if you see, you'll see it in MAC addresses, you'll see it in memory locations, and usually when it's listed, it's going to start off with a 0x, and then it'll have the hexadecimal number like 0 alpha foxtrot, right? That would be an example. So that's hexadecimal in a nutshell. All right. So those are the and of course we all know decimal too. All right. So that being said, let's move on to the next thing where we talk about actual bits and bytes. As I said, a bit is that 1 or that 0, right? Every single 1 or 0 is a bit. So early on in computing science, what they did was if you had 8 of them, so we're going to do 8 bits is going to be 1 byte. Okay, so all a byte is 8 bits. All right. Now a nibble is going to be 4 bits. That's also a byte is 8 bits. 4 bits equals a nibble. All right, so that'll be a nibble. Nibble. So nibbles aren't really used all that much. You'd use it to calculate hexadecimal addresses because every hexadecimal number is 4 bits. There you go, right? Because if I do, guess what? If I do 1, 1, 1, 1, that's going to equal 15, right? So there you go. So that's 15, right? 8 plus 4 plus 2 plus 1 is 15. So that's going to be that's your maximum, right? And 0, 0, 0, 0 would equal 0. So you could represent any hexadecimal number with 4 bits. All right. Anyway, so the important thing here for us is to know that there's bits and there's bytes. A bit is every single 1 and 0. Often transfer rates and particularly network transfer rates are represented in bits per second, and you're going to see that. Let's say if we have 100 megabits per second, what you would see is you'd see m lowercase b s, right? Now, when we buy our thumb drives, for example, right? If we buy a thumb drive, it's going to, a really cheap thumb drive. All right, we'll keep it with the mega. It has 900 megabytes. What's going to have is bytes. Usually we do our storage in bytes. And when you see that, it's going to be capital B, megabytes. Okay, so keep that in mind. Storage is usually kept in bytes. Transfer rates is usually in bits. All right. All right. So let's talk about the next subject and make that go away. Yeah, sure ain't. Whoops. All right. Storage units. All right, so I did mention megabytes, and here's mega right here. We have kilobytes and kilobits and all that stuff. This is what the storage units represent essentially. Okay, so it's going to be, and I mentioned zeta before, by the way. As you can see, it's rather huge, right? So if I say I have a kilobyte or a kilobit, whatever, it means I have 1,000 of them. That's all that means, right? So, by the way, also, so if we had 8 K and then capital B kilobytes, right? That'd be 8,000 bytes, but it would also, I I messed that up. If we had one, let's just do one to keep our math simple. If we had 1 kilobyte, right, that would of course mean 1,000 bytes, right? This is writing slow, and I apologize for that. 1,000 bytes, all right. But that would also equal 8,000 bits, all right, or 8 kilobyte bits. Okay, so that's one thing to keep in mind. All right. Also, what we did is a megabyte. Essentially, it's going to be 1,000 to the second power. That's going to be a megabyte. Usually, rule of thumb is there's 1,000 kilobytes or kilobits in a megabyte. Gigabyte, again, you're going to have 1,000 of those. Terabyte is 10 to the 4th. A petabyte is going to be 10 to the 5th. Essentially, every time you have 1,000 more of something, you're going to jump into the next storage unit. All right. So again, when you hear the term exponentially larger, this is what we're talking about. The storage units are measured exponentially larger. Okay. Every time you add another 1,000 of something, you add a power of 1,000. We jump over to the next system. All right. So just giving you an idea of what's going on underneath. I don't think it's critical to well, it is nice to know this. All right. So let's talk about operations, actually OS operations, memory and storage management. We talked about this earlier in theoretical. This is one of the big things that an operating system does. This is critical to its core component. Now keep in mind that storage and memory are written to, read from, changed, moved, add constantly. Part of this too is the operating system has to reserve part of the memory as its own. Every one of these little blocks is kind of a sector, and they all have their own address space. That's what this does. What the CPU actually does, right? It actually sections off the entire both storage and memory, and it has address locations, and those address locations is how it knows where to do it. Well, where to retrieve the data or write the data. So anyway, part of the operating system, it has to cordon off and say, hey, this area is for the operating system. Now, as a program runs through and it's going to get bigger and bigger and bigger in memory, I'm looking at you, Chrome, but as a program keeps eating up more and more and more and more memory, what's going to happen is it's given a little section space. It's, I'm going to need a little bit more. Okay, well, here's a little bit more. I'm going to need a little bit more. Okay, well, here's a little bit more. Now, if an operating system's not careful and it says, hey, I need a little bit more, and there's just a little bit of overlap, that little bit of overlap right there can cause the entire operating system to crash, right? If we're changing memory data for the operating system while it's operating, you're pulling the rug out from underneath it, and you can actually crash the entire operating system. Never mind the application that was taking up more and more and more. Also, you have malicious programs, right? If you have a piece of malware, a well-written malware that understands machine code and understands how it addresses would love to find out this location. What is the location that is reserved to me? So it might actually go out and try to write to random parts of the memory, and when it starts getting denied, it goes, aha, I'm not allowed to go in there, so I really want to go in there, right? And then the operating system has to do its best to try to keep refusing this program from being able to write. It will do all kinds of tricks. It will try to utilize machine code, the actual code that the CPU uses, to try to write this, which kind of runs a little bit underneath a lot of the security measures. So just keep that in mind. So that's a big part of the operating system. Also, the storage has the same thing, right? We have lots of parts of storage that's been sectioned off for applications to store their data, for the operating system itself to be stored and booted from when it returns. We'll have DLLs in there in the case of Windows, right? We're going to have sys files. We're going to have all kinds of critical files in here. That if those system files get written to, the next time the operating system reboots and loads it into memory, it could change the critical way the operating system runs. All right, so that's all important to keep in mind as well. All right, so that being said, let's talk about another complex concept of operating system management, which is processor. First of all, let's talk about a couple things. So I mentioned this a little bit before. When the operating system sends jobs to get encoded into the CPU, it's going to send this stream of bits, okay, as what we call a thread, okay? And this thread is going to come through and try to be read. Now, the CPU has what's called a clock cycle, okay? That clock rate, excuse me, that clock rate is, best way to think about it is a cycle. And it's going to come in and keep spinning and spinning and spinning and taking this data in. Okay, and as it takes in the data, the control unit is going to do the process for it. It's going to do the arithmetic. It's going to do the logic, and then of course it's going to spit it out as output. Okay. So when it does that, obviously how fast that goes is really important to the user. It's a selling point. Intel, AMD are very fascinated in making this go as fast as possible, as well as Microsoft. They would love their operating system to be as efficient as possible. Okay, so again, oh, by the way, I had this illustration a little bit earlier and didn't explain it. This is my, by the way, my highway versus the dirt road, right? Is, again, I want to make this point repetitively so that it might stick a little bit better. Storage has a dirt road, a windy dirt road that might get muddy and have lots of potholes, while memory has that nice, beautiful highway that you can go really fast on. All right. Anyway, back to the processor. So one core concept is the bits. All right. When you have a 64-bit processor, 32-bit processor, 16, 4, you can actually have a 4-bit, 8-bit processor. That's what's called the word size, or how what the basic block that it takes in here. I try to draw it here with these little blocks. That's how many bits at a time it takes in when it takes it into the cycle. Most processors nowadays are 64 bits. We're going to talk about this again in hardware architecture. Because we have 60, and certainly software architecture, because we have 64-bit operating systems, or operating systems running on 64-bit processors, but we still want to support our 32-bit programs because that's legacy. Older processors were 32-bit. So we're going to talk a lot about that down the road. But anyway, so what that's referring to is the word size, or how big of a processor when we take it in. When a processor takes in a bigger word size, it's going to require more circuitry in the processor, which would make it bigger, which would draw in more power, which would create more heat, which is all kind of problems, and then we're going to talk about that in a little bit more for modern day computing, because most computing is done, at least personal computing is done on laptops, and power and heat are a big deal, and size as well. Anyway, that's the basic concept. Okay, we have a clock rate that kind of spins, takes in this thread. Okay, and that thread is going to be taken in chunks of either 64 bits, which are most modern day processors, 32 bits, which is a lot of old legacy software, still runs in 64-bit. A lot of our programs still run in 32-bit. Matter of fact, VMware is going to run in 32-bit. The free version that we're using is going to run 32-bit. 16-bit, 8-bit, 4-bit. There are lots of 4-bit, 8-bit, 16-bit processors out in the world. They don't run desktops or operating systems, but you might see them in appliances or small HVAC devices, heating, air conditioning. Heating, ventilation, air conditioning. But anyway, they might be kind of, Internet of Things, smaller processors. They're still out there because, again, they're very small and very efficient, and they don't put out a lot of heat. Continuing on talking about processors. So we talked about that thread, and we're talking the constant competition of making a faster, better processor. In the early days, we only had one CPU, and you could go by clock rate. My very first CPU that I bought with my own money was a 133 megahertz processor. It was a single processor, a single core, just running at 133 megahertz. So the clock rate was 133 megahertz. It would take in that the thread at that rate, and it would process it as you know, as quickly as it could, which wasn't all that quickly. So then there was this grand race between AMD and Intel and Moore's Law. Moore's Law said that processing, that clock rate was going to double every 2 years. And for the most part, Moore's Law from during the 90s and early 2000s was spot on. But what eventually happened, two things. What the bigger problem there was especially were getting faster and faster. They were consuming more power, and they were putting out more heat. That's a problem, again, especially for laptops, but mobile phones. And there was just a general need to make processors consume less power and put out less heat. Okay, so one trick that was used early on that we need to talk about is hyperthreading. All right. What hyperthreading does is there's another factor in here that I haven't been drawing. Matter of fact, I'll erase and start over. We have this another entity, which is the process of the OS, right? That OS is what generates that thread. The thread management, the processor manager, is what generates that thread, right? So, operating system. So that operating system is actually what's going to generate that thread and send it to the CPU. One trick that both the CPU can support and the operating system both has to support it is what's called hyperthreading. Okay, and what hyperthreading does is we kind of trick the OS, and the OS is playing along with the trick. And software-wise, we treat the CPU as if it's two, so you kind of send two separate threads. And what the operating system does is it sends two threads. And what it's able to do is the software, this hyper-threading process is kind of a encapsulating process, right? And that encapsulating process is going to send a thread at a time in. And if there's a thread that it's looking at that's not as real time, it doesn't really need to be processed immediately. And keep in mind, by the way, we're going to talk about this a little bit in a little bit when we talk about the history of operating systems. Multitasking was a big deal when it came out. Matter of fact, we still talk about it with our phones. Can that really multitask? A computer doesn't really multitask, right? A computer takes care of one thing at a time, or certainly during this time period when there's only one core. And what it does is it switches between jobs so quickly that us stupid humans think it's doing two things at once. So when you're typing away a word, it's still watching a video. You think you're doing two things at once, but actually the computer's doing it. So it's switching between the two jobs so quickly that you think it's going on simultaneously. Well, with the hyperthreading, what's able to do is looking at these threads, it's able to sit there and say, oh, that's got to be more real time. We can push this off to the background process. It's able to manage these things. It's really a trick. It's a sleight of hand to cause thread processing to go faster. Okay. Next. If we look at multicore, okay? Multicore processors, what they do is you have one single CPU, but you're able to have multiple cores. Those cores are all going to have their own control units. They're all going to have their own arithmetic units, right? And they're going to process data, okay? Now, again, we have the operating system, right? Right, there's the OS, and it's going to send its threads or hyperthreading. I like to keep it the concept simple and just say it's a single thread. Hyperthreading, it's still a trick. It is a single thread, but they mark them differently, and they're it's very technical. But it's going to send a thread into here, right? And this CPU. The CPU itself is kind of a level. That's why when you have 4 cores, there's going to be a little bit of overhead here. There's a little bit of management overhead. But this CPU, the overarching multi-core structure, is going to divvy up the job essentially, right? It's going to say, okay, and part of this thread, by the way, is jobs are kind of lumped together. So it's going to send one job over to here. It'll send another job over to here. It'll send another job over to here. It'll send part of that thread over here, right? And as it comes out as output, this CPU core again needs to recompile it and put it back out as a single stream of output. Okay, but it has 4 different cores. All right. again, during the great race of the early 2000s, Intel kind of announced it's like, okay, we're done building faster and faster processors. What we're going to do is we're going to do multi-cores, right? And we're going to kind of build this system out where we have this overarching architecture and multiple cores on it. By the way, this would be a 4-core structure. If you have a multi-core system that has 4 processors, that's what we're talking about. It has 4 cores. Excuse me. It'll list as 4 cores. These are the 4 cores. Anyway, so AMD kind of stuck with the bigger and better and badder and faster processors, but of course, bigger is not always better, and power consumption and heat production were serious issues. And now everyone, including AMD, does multi-cores. This is the winning strategy. Essentially, Moore's Law has been busted because these cores are running at lower hertz than what if you had one big massive processor doing it, right? So that's where we're at. And the stumbling block wasn't making processors faster per se. If we wanted to keep building bigger and more power-hungry processors, we could have kept Moore's Law going. It's not completely broken, but the hard physics and reality of heat and power came in size. Anyway, so long story short, multi-core means you have multiple cores on one chip. And that chip then takes the thread in, divvies up the job to the multiple cores, and puts out another thread. All right, let's talk about finally the last concept. And I have to close that out. And then the last concept would be multiprocessor. All right, a multiprocessor system is going to have, and you can have multi-cores, by the way. You can have a multi-core, CPU processors. But essentially, there's going to be still only one OS, right? That OS, again, is going to... I meant to hit... So, the slide jumped on me. And all right. So, the operating system, there's only one operating system still, right? There it is. There's my operating system with a funky looking O. There we go. Rock and roll looking O. So what happens is the operating system is going to recognize multiple CPUs, and it's going to start sending its own threads to the CPU. It has to manage that. Again, so if you have multiple CPUs, there's going to be an overhead to it. Again, when this, by the way, the CPU architecture would be multi-cores, it would then divide up the job even further into multiple cores and then come out as a single output stream, right? So the operating system is going to send out the threads to the multiple cores. All this takes up overhead, by the way. So if you have multiple CPUs, it won't be as fast as if you have one CPU that had the equivalency. So if you had a choice between let's just say 2 CPUs running at 400 megahertz versus a 800 megahertz processor. Technically, the 800 megahertz processor would be faster because this whole dual threading and splitting it up, splitting up the job would actually take a little bit of overhead. Okay. So multiple CPU has multiple CPU architectures. Multi-core has multi-cores within our architecture, and hyperthreading is a technique, a cheat used by the operating system and the CPU to make it look like, or make it treat it somewhat like it has multiple cores. Okay, so next let's talk about information or input-output. All right, so again, input-output. This is what's going to be the ultimate judge on an operating system, right? This is how the user interacts with the operating system. We're going to start talking about that. What do the users think about this operating system, right? So there's a couple different interfaces that you should be aware of. Command line interface, a great example of that would be PowerShell. Let me bring that up on my machine. There you go. This is my PowerShell. This is me compiling code, actually. This is DOS, or not DOS, but this is PowerShell right here. So this is command line interface, right? A lot of users don't like it, but it's an important I'll go to the root, my hard drive. There you go. There's my root, right? It's quick, it's fast, it's easy. The more you spend time with an operating system, the more you clamor for a CLI because it's fast. It's actually one of the fastest ways to actually do things on an interface. I know there's a steep learning curve, so people don't prefer it, but understandable. All right, but that's a CLI. It's a command line interface. I type in commands, I get output, and I keep interfacing. A GUI is what we got right here. This is actually a graphical user interface. Have buttons. I can click on things, right? I can control things. I can make my pointer do funky things. There we go. So anyway, long story short, that is a GUI, a graphical user interface. Again, multitasking is huge on that, right? I have my windows open. I have multiple windows open. That I can bring in other things. Here's Visio, where I was drawing that in. I can make this smaller and give a presentation while at the same time I'm working on my Visio drawing, right? So long story short, that's one advantage of certainly of GUI as compared to CLI. There's also voice user. Well, there you go. And my password will expire soon. So we have voice, but there's a problem with GUI too. It's more apt to like misclicks and mishits. So when you're programming for a GUI, you have to account for that. We also have voice user interface, which is of course, OK Google, right? So now my watch and my phone have just activated, right? That's voice line interface, right? That's when you actually talk to your systems, okay? So the Google Assistant, Siri, Alexa, and I guess I'm duty bound to mention what's the name of Cortana for Microsoft. All right, so we also have touchless user interface. You might want to think of that Tom Cruise movie there. Minority Report. You put your hands up, you could scroll through screens, you can move your hands, it'll recognize your hand gestures either through camera or some kind of sensor, and you're not touching anything, you're just kind of by gesture you're able to control the system. Also by looking too, it can track your pupils to see where you're looking. So there you go. And of course we have not only do we get input output by our user, but we also get what we have to show them. So we have peripherals like video and of course audio, both very important, right? Graphics are very important, which leads me finally to our operating systems. What do we expect from our operating systems? Well, we want them accessible. When I say they're accessible, I'm saying we want devices to work on it, right? We don't want to plug in a device and say that hardware doesn't work with your current operating system. It just refuses to work with that operating system, right? We want our operating system to be accessible from multiple devices. Is when we say accessible, not necessarily about the user. Okay, we want our system to be fast. Right? We want it to be as fast as possible. Efficiency is good. Obviously, the hardware is only as good as it can be, right? You're limited to what the hardware is of the day. But you can't just release an operating system that's the prettiest and have all these animations and 3D 3D thing, because it'll slow down the machine, and users don't like that. They want a snappy operating system. They want to be intuitive. They want to know where to click. They don't want to be searching around for menus. They don't want to be scratching their heads. They don't want a steep learning curve. Okay, so they want their system intuitive. They want it pretty. They want transparencies. They want those 3D animations. Well, they don't really want some do, some don't want 3D animations, right? I mean, look at what I did right there. I'm talking about how efficient CLIs are, and I increased this isn't the default of what PowerShell looks like, right? The default is, the default would be a solid background, right? So I added transparency. Well, that's going to eat up more memory, right? So people want their prettiness too, right? Obviously, they want it stable. They don't want it crashing, and they want it secure. They want it. They want to be sure that the information that they put in there won't get corrupted or read by someone that's not supposed to read it. So accessible, which could cause stability issues, right? They want it fast, which the prettier you make it, aesthetics, it's going to be slowed down. And by the way, accessibility can also affect the speed and the efficiency, right? If I'm told this is going to be the hardware every time, then I can make a really fast operating system because I don't have to put in all these subroutines to handle all these other different variables, right? They want it intuitive. Okay, that's cool, but intuitive might be that might be affected by the aesthetics or certainly security, right? If I make something more secure, it's going to be less intuitive because they have to click through more things, right? We talked about aesthetics. It's going to slow down the machine, right? It might make things less accessible too. Certainly, possibly make things less stable. Stability would affect aesthetics, right? I might have to sit there and say, listen, transparency is nice, but it might cause the graphic card to eat up too much memory and cause the whole system to crash, right? So stability, and of course they want security. Well, intuitiveness will certainly affect security, right? If I make my system more intuitive, the most intuitive system in the world would simply just do whatever you asked it to. Well, that won't be very secure because I need to verify who you say you are. I need to put safe checks in. I have to log everything. So security is a big part of the operating system. So again, all these things conflict with each other. Welcome to IT, right? We're about accessibility and we're about security. So that's one of the problems we have. We have a conflicting message over mission. But we can deal with it. So again, users want accessible, fast, intuitive, pretty, stable, and secure operating system. So good luck with that. Have fun storming the castle. So that's the quick lecture on operating system operations, or how it actually does what it's supposed to do. So I'll talk to you again later.